NENOMATICA, where mathematics meets YouTube excellence. Scientific notation. Welcome to this educational video about scientific notation. Let's explore how we represent decimal numbers in a standard format. In general, the scientific notation for any positive decimal number is in the form of a times 10 raised to the power n, where it is between 1 and 10, and n is an integer. Let's understand the rule. For scientific notation, we need a coefficient between 1 and 10 multiplied by a power of 10. Let's look at some numerical examples. These will help us understand how to write numbers in scientific notation. Example. Here we have 125 equals 1.25 times 10 to the power of 2. This satisfies our rule because 1.25 is between 1 and 10, and the exponent 2 is an integer. Let's look at another example. Here we have 0.125 equals 1.25 times 10 to the power of negative 1. Again, 1.25 is between 1 and 10, and negative 1 is an integer. Let's try a step-by-step conversion. We'll convert the number 3,456 to scientific notation. Step 1. Move the decimal point to get a number between 1 and 10. For our number 3,456, we move the decimal point left by 3 positions, giving us 3.456. Step 2. Count how many places you moved the decimal point. We moved it 3 places to the left, so our exponent will be positive 3. Step 3. Write the number as a coefficient times 10 raised to the appropriate power. Thus, 3,456 equals 3.456 times 10 to the power of 3. Let's try one more example, but this time with a number less than 1. We'll convert 0.0078 to scientific notation. Step 1. Move the decimal point to get a number between 1 and 10. For 0.0078, we move the decimal point right by 3 positions, giving us 7.8. Step 2. Since we moved the decimal point 3 places to the right, our exponent will be negative 3. Step 3. Write the number in scientific notation. Thus, 0.0078 equals 7.8 times 10 to the power of negative 3. Today we're going to learn about ordering scientific notation. Let's start with an example. We need to arrange these numbers from smallest to largest. To compare these numbers, we'll convert them all to decimal form. Then we can easily arrange them from smallest to largest. Let's convert each number to its decimal form. For the first number, 1.5 times 10 to the negative 2 equals 0.015. For the second number, 1.2 times 10 to the 6th, which equals 1,200,000. For the third number, 5.35 times 10 to the negative 3, which equals 0.00535. For the fourth number, 3.7 times 10 to the negative 2, which equals 0.037. Now, let's compare all these decimal numbers. Obviously, 1,200,000 is the largest. Among the remaining numbers, we have 0.037, 0.015, and 0.00535. The smallest number will have the smallest value, which is 0.00535, followed by 0.015, then 0.037, and finally 1,200,000. Finally, let's write our answer in scientific notation, ordering the numbers from smallest to largest. Let me show you another method to compare numbers in scientific notation. We can compare the exponents first, and then the coefficients. If two numbers have different exponents of 10, the one with the smaller exponent is smaller. If they have the same exponent, compare the coefficients. Let's look at our example. The mass of one electron is approximately 9.1 times 10 to the negative 25th grams. We need to find how many times the mass of a 2,549-ton object is greater than the mass of an electron. Let's start our solution by writing down what we know. The mass of an electron is 9.1 times 10 to the negative 25th grams. Now, let's find the mass of our 2,549-ton object. First, we need to convert tons to kilograms. 1 ton equals 1,000 kilograms. Next, we need to convert kilograms to grams. 1 kilogram equals 1,000 grams, which is 10 to the power of 3 grams. Let's rewrite this using the laws of exponents. We know that 10 to the power of 3 times 10 to the power of 3 equals 10 to the power of 6. Now, we need to find the ratio of the object's mass to the electron's mass. We divide the mass of the object by the mass of the electron. To divide these numbers, we'll separate the coefficients and exponents. For the coefficients, we divide 2,549 by 9.1, and for the exponents, we subtract -25 from 6. Now, we simplify the exponent calculation. 6 minus -25 equals 6 plus 25, which gives us 31. Let's calculate 2549 divided by 9.1. This gives us approximately 280.1. We can write this result in scientific notation as 2.801 times 10 to the power of 33. Therefore, the mass of our 2,549-ton object is approximately 2.801 times 10 to the power of 33 times greater than the mass of a single electron. This demonstrates the incredible difference in scale between everyday objects and subatomic particles. Let's look at this example involving the mass of an electron and a hydrogen atom. We're given that the mass of an electron is approximately 9.1 times 10 to the -28 kilograms, and the mass of a hydrogen atom is approximately 1.7 times 10 to the -24 kilograms. Can we visualize how small these numbers are, and which one has more mass, and by how much? Let's find the ratio of the hydrogen atom mass to the electron mass. Slide in, we substitute the given values into our ratio. The mass of the hydrogen atom is 1.7 times 10 to the -24th divided by the mass of electron, which is 9.1 times 10 to the -28 kilograms. Now we can separate the coefficients and the powers. We have 1.7 divided by 9.1 times 10 to the power -24 minus -28. Let's simplify the exponent. -24 minus -28 is -24 plus 28, which is +4. Now, let's calculate 1.7 divided by 9.1. This gives us approximately 0.187. We can write this in standard scientific notation by adjusting the coefficient and exponent. 0.187 times 10 to the fourth is equal to 1.87 times 10 to the third. This means the hydrogen atom is approximately 1,870 times more massive than an electron. Let's look at an example. The speed of light is 300 million meters per second. What distance does light travel in 100 hours? First, let's convert 100 hours to seconds. We know that 1 hour equals 3,600 seconds. Now we can calculate the distance. We multiply the speed of light by the time. The distance equals 300 million meters per second times 360,000 seconds. Let's convert these large numbers into scientific notation to make the calculation easier. 300 million is 3 times 10 to the power of 8, and 360,000 is 3.6 times 10 to the power of 5. When multiplying numbers in scientific notation, we multiply the coefficients and add the exponents. In scientific notation, the coefficient should be between 1 and 10. Since 10.8 is greater than 10, we adjust it to 1.08 and increase the exponent by 1. Welcome to this physics lesson, where we'll solve an interesting problem about the mass of Earth compared to its atmosphere. The question asks, how many times heavier is the mass of the Earth compared to the air in its atmosphere? To solve this problem, we need to find the mass of the Earth's atmosphere and compare it with the known mass of the Earth itself. Let's start by thinking about how to calculate the mass of the atmosphere. We know that air pressure at sea level on Earth is about 1 kilogram per square centimeter. This means that for each square centimeter of Earth's surface, there's a column of air with a mass of 1 kilogram pressing down on it. So if we can determine the total surface area of the Earth in square centimeters, we'll know the total mass of the atmosphere in kilograms. Step 2. We need the Earth's surface area. Reference books tell us that the Earth's surface area is approximately 510 million square kilometers, which can be written as 5.1 times 10 to the 7 square kilometers. Now we need to convert this to square centimeters, since our pressure is given in kilograms per square centimeter. Step 3. Converting square kilometers to square centimeters. First, let's recall that 1 kilometer equals 1,000 meters. And 1 meter equals 100 centimeters. So 1 kilometer equals 1,000 times 100, which is 100,000 centimeters. For area conversion, we square these values. So 1 square kilometer equals 10 to the 10th power square centimeters. Step 4. Calculating the Earth's total surface area in square centimeters. We multiply the Earth's surface area of 5.1 times 10 to the 7th square kilometers by 10 to the 10th square centimeters per square kilometer. This gives us 5.1 times 10 to the 17th square centimeters for the total surface area of the Earth. Step 5. Now we can calculate the mass of the atmosphere. Since each square centimeter of Earth's surface has 1 kilogram of air above it, the total mass of the atmosphere is equal to the surface area in square centimeters. To convert from kilograms to tons, we divide by 1,000. So the mass of the atmosphere is 5.1 times 10 to the 14th tons. Step 6. Now let's compare with the Earth's mass. The mass of Earth from scientific references is approximately 6 times 10 to the 21st tons. Step 7. Finally, we calculate how many times heavier the Earth is compared to its atmosphere. We divide the mass of the Earth by the mass of the atmosphere. 6 times 10 to the 21st divided by 5.1 times 10 to the 14th. This gives us approximately 10 to the 6th, or 1 million. In conclusion, the Earth is approximately 1 million times more massive than its entire atmosphere. This means that the option D, 10 to the 6th power, is the correct answer. This massive difference in weight helps explain why Earth's gravity can hold onto its atmosphere, and also why atmospheric pressure is relatively constant across the Earth's surface. Welcome to our lesson on reaction rates and temperature dependence in chemistry. Today we'll explore how temperature affects the rate of chemical reactions and solve a fascinating problem about combustion at different temperatures. When we discuss chemical reactions, one of the most important factors affecting reaction rate is temperature. The relationship between temperature and reaction rate is governed by a fundamental principle. For every 10 degrees Celsius increase in temperature, the reaction rate approximately doubles. Let's consider a specific problem. We know that at 600 degrees Celsius, a gram of wood burns in 1 second. The question asks, how long would it take for a gram of wood to burn at 20 degrees Celsius? And how many years would that be? To solve this problem, we need to determine how many 10-degree drops there are from 600 degrees Celsius to 20 degrees Celsius. That's a temperature difference of 580 degrees, which means 58 steps of 10 degrees each. For each 10-degree decrease, the reaction rate is halved. Since we have 58 steps, the rate will be halved 58 times. This means we need to calculate 2 raised to the power of 58. Now, if the wood burns in 1 second at 600 degrees Celsius, then at 20 degrees Celsius, it would take 2 to the power of 58 seconds. Let's calculate this value. 2 to the power of 58 equals approximately 2.9 times 10 to the power of 17 seconds. To convert this to years, we need to divide by the number of seconds in a year. 1 year contains approximately 3.15 times 10 to the 7 seconds. So, dividing our time by this value gives us approximately 9.2 times 10 to the power of 9 years, or about 9.2 billion years. To give you a sense of perspective, the age of the universe is estimated to be about 13.8 billion years. So it would take almost as long as the universe has existed for the wood to burn at room temperature. This illustrates the dramatic effect of temperature on reaction rates. So what have we learned? The rate of chemical reactions is heavily dependent on temperature. Though wood combustion is spontaneous at room temperature in theory, the reaction proceeds so slowly that it's practically unnoticeable. This is why we need to add heat to start a fire. We're accelerating a natural process that would otherwise take billions of years. To recap our solution, we calculated that the temperature difference from 600 degrees Celsius to 20 degrees Celsius is 580 degrees Celsius, which gives us 58 steps of 10 degrees. For each step, the reaction rate is halved, resulting in a total factor of 2 to the power of 58. This means the burning time would be approximately 9.2 billion years, almost the age of the universe itself. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.